Welcome. Now we will be talking about the time series of different models. So far we have just looked at some of the ARP models. We will do some of the examples later, but let us define the problems first. AR, ARMA and MA process, which were integral part of the stationary time series which we introduced in the last class. The concept that we will be covering today are the AR process, then MA process and then ARMA process. So, AR is basically autoregressive process, MA is moving average and ARMA is autoregressive moving average process. Now today we will be explaining the moving average part. Moving average. Okay. So, how do you define a moving average? Moving average, let us take the first one, so it is called MA. So, let us define MA 1, simple to start. So, you have yn, okay. Then you have A1, En minus 1 plus E of n, right. That is the only thing that will be coming into picture, right. So, this part is there anyway, because that is the randomness, but now yn does not depends on previous value of yn, but is previous value of my randomness. Okay. Now, in our channel how much it is effective, it is doubtful, but it is just as per our definition. So, whether we really need it for our channel model, that is a secondary question, but as per the time series this can be useful. Now, similarly, this is MA 1 model and I can generalize it. So, let us say I want to have a MAQ model. So, you have A1 En minus 1 plus E2 A2 E n minus 2 plus dot dot AP or AQ plus En. So, this is the MAQ model. So, here you can see it depends on q number of previous disturbance or previous innovative process innovations or the random values. So, that is the moving average, it is a MAQ model. So, this is your MAQ model. Okay. Now, given an MAQ model, how do I get some sort of a spectrum analysis, because that is our ultimate goal, right. Again we can use the backward operator, because that is easy to easy to deal with, right, instead of a autocorrelation. Autocorrelation also you can use it, but let us use the backward operator. That is what we are comfortable with here in this case. Let us the definition remains the same. If B En comes, it is nothing but En minus 1. So, that definition is anyway there. So, if I express the whole thing in terms of backward operator here, so how can I express it? So, this will be yn, okay, yn is equal to A1 E A1B plus, can I say, A2B square, because it is just two operator, AQ BQ plus En. Sorry, there is small mistake here. Plus 1 into En. This is what it is, right, correct. So, what is my ultimately, again I come back, yn by En, what it would be? It is like 1 plus A1B A2B square AQ BQ. Same thing, same linear system of linear equations. You have an En, you give this Z of B, you get Yn. Okay, and you can see this is an FIR filter, just like an FIR filter. So, how do you get a spectrum of a FIR filter? Replace B by e to the power minus j omega, right. So, you get z omega and calculate this one. So, calculate z omega square. So, what does it give? It gives you the power spectral density. I am done. If somebody gives me power spectral density, I am really done, because that is the part I am looking for. Okay. So, I have to just replace this, instead of B I have to write e to the minus j omega and then take the conjugate of it and take the just multiply it. That means j of omega and j star of omega, you get it, you get the power spectral density of it. And if you know power spectral density, you know how much this bandwidth would be. You can exactly know how much the bandwidth would be, right. So, this part you want to make it. Okay, this is very standard process. Similarly, let us go to the ARMA process. This is the ARMA process. So, what is the ARMA process? So, it is a mix of autoregressive process and moving average process. Okay. So, it has a autoregressive part. So, if Yn is my data of observation, so it will have a autoregressive with respect to p order, and it has a moving average with respect to q order. Okay. So, it would be say A1 Yn minus 1 plus AP Yn minus 1, sorry, AP Yn minus P. So, this is the this part is your AR part plus now there will be a MA part. So, let us put a different notation E n minus 1 plus dot 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 BQ E n minus q. Okay. Now, this part is your MA part. Okay. Apart from that, obviously, you will have a noise. The noise, of course, noise meaning the current noise. This is the one. So, this is your ARMA PQ model. Okay. Now, if you go through the, if you want to get the autocorrelation function of such ARMA process, is very complicated. It is not easy to get it, right. So, best way to get the power spectral density, you put a B operator, replace B equal to the power minus j omega, and then take the conjugate and multiply. You get the spectrum, at least you get the power spectral density part, and that is it. You are done. So, now the same thing I want to express it in terms of the B operator here. Let us do that. So, take the y part in the left side. So, this would be A1 Yn minus 1. I am taking all y pi left, y side, y component left side and e component in the right side, minus A2 Yn minus 1 minus 2 AP Yn minus P, one sided, equal to left side, right side we will have all the e component. So, what are that? B. So, this would be B1 E of n minus 1 plus dot 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 B of q E of n minus q plus En. This is what I am getting it. I am just rearranging it. Now, I use a B operator, use B operator on that. So, how do I express it? So, this will be 1 minus A1 into B minus A2 into B square minus A of P B to the power P, correct. just into y1, just use a B operator. Similarly, I will have the similar kind of things, B1 B plus dot 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 B cube B to the power cube plus 1 n. This is what is happening. Again, you create some sort of a input output relationship. What will I get? Say yn by en. What will I get? I will get some sort of a polynomial by polynomial. So, it is as if like some sort of a IR filter kind of things. I will get something like that, or probably I will beautify this one plus this one. Similarly, I will get this other one A1B dot 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 minus AP B to the power P and so on and so forth. So, this is my filter. You can think of it as a filter. Okay. So, this is my filter. This is my complete input output. So, this is the filter with complete input output relationship. Okay. Now, whether it is stable, that you have to see, you have to do a pole 0 analysis and see whether it is stable or not, but that is a secondary question, because if it is not a stable, of course, there is problem. So, and that drives us how exactly how exactly the value of B1 to BQ or A1 to AP should be there. Okay. So, that really drives us whether it is really a stable or it is not a stable part. Okay. But whatever it is, let us assume it is a stable and let us assume it is also a causal system. If that is the case, then I can think of a spectrum very easily, right. So, what is the, how do you get a power spectral density of such system? So, this call it this whole this whole quantity within that red box, I call it Z of B. Okay, that is your that is your filter part. So, how do you get a power spectral density? Replace B by e to the power minus j omega, you are done. So, it is very easy to get the power spectral density of such system, and you can easily know how much your Doppler shift. But the crucial point that I am trying to convey here is that the B1, BQ, A1, AP, these coefficients, how do you really get it? They are not easy to get it. They have to come from lot of measurements, they have to come from lot of other things. So, they are not something which are very straightforward, but there are ways to do that. So, you can create a model and you can try to do some sort of an estimation, that is okay, but there is a way to estimate these coefficients. So, given the fact that you can estimate these coefficients well, I can very well create a time series model. Okay. Now, let us go back to our channel part, because this is where we started with. So, what we started with? We started with our channels which are say H0 to say H of L minus 1. So, let us say I have a channel which has L number of coefficient, frequency selective channel, L number of coefficients I have. Now, this is only at a particular time m. So, when I change it to m plus say 1, m plus 2, I can think of the whole thing as a time series modeling. Like for example, now the time series modeling in which direction? So, there is one direction here and there is one direction here. This is also times. If you look at the right side, this is also time series, right, but in a tau domain, in the delay Doppler, in a delay spread domain. But when I look at the vertically, it is basically your Doppler domain. So, both are actually time series. Now, this one, the right one or the right and left side which is coming in the below direction, that gives us a flavor of the Doppler spectrum. So, this gives us a flavor of the original coherence bandwidth spectrum. Now, there are another issues. Point here is that you have one time series here, and like that you have L number of time series, right, because there are L coefficient and each and every coefficient I can think of it as a time series in the Doppler's case, right. So, that means H 0 will vary over time, H 1 will also vary over time, and so on and so forth till H L minus 1. So, H L minus 1 will also vary over time, and each and every time, each and every each and every taps we have so far tentatively assume they are kind of uncorrelated, independent. So, that means I can say there are L number of time series parallelly going on. I can think of that way. So, that means this H 0, then this so I can say this is H 0 m, this is H 0 m plus 1, this is H 0 m plus 2, and so on and so forth. I can also think this is H L minus 1 m, H of L minus 1 m plus 1, and so on and so forth, H L minus 1 m plus 2, and so forth. So, there are L number of such time series parallelly going on. Okay. Now, the question would be the effective bandwidth that we are seeing it, right, is due to what? Is it all individually, or is it the summation of all, or is it kind of a different way? Okay. So, what I am trying to say that if this is a time series, this will give you a power spectral density, it will have some power spectral density 1. If this is a time series, this will also give you another power spectral density, well, minus 1. The question that arises, are all these L taps give you the same power spectral density or not? We do not know that, right. So, the effective change in my channel that we would see is neither due to PSD 1 or neither due to PSD L minus 1, it is a composite, right. It is basically each and individual tap is changing that. So, it is basically a composite effect that I am seeing. Okay. So, it may happen that this changes say up to 10 kilohertz, whereas this changes only up to 1 kilohertz. Well, the effect will be more prominent somewhere here, right, because that changes. So, I will say bandwidth is getting shifted more towards 10 kilohertz, but that is in between 1 kilohertz changes also happen. So, you can't really say exactly which one will take the dominance, whether it is 1 kilohertz or 10 kilohertz. Tentatively 10 kilohertz will have something to say more, because it shifts more there, right. Now, what if all these H 0 H L minus 1 have the similar kind of statistics, all have the similar statistics? That may happen. That precisely we will be discussing in the millimeter wave, because in millimeter wave you can't simply say that just because that H it is sitting at H L minus 1, it will have a very low power. You can't really guarantee that, because everything is in an indoor environment. Okay. This all depends on how the power absorption at the far off places happens. So, it is not a very outdoor environment. Outdoor environment, yes, this H L minus 1, you can see the taps really going down, but when it is a millimeter wave, you can't guarantee. You can't guarantee that the powers will be going down very drastically. So, there may be even significant power at some instance of time, not just at H 0. So, there if you have that kind of scenario, it is more or less, you can say more or less they can have a almost the similar statistics. So, the effect will be same for all of them, but when you have a different scenario, in case one shifts only 1 kilohertz, another shifts 10 kilohertz. So, what is the effect? Is it 10 plus 1 kilohertz, or it is 10 minus 1 kilohertz? No, the effect will be the one which shifts maximum, right, because that is the one which shifts maximum. The others will be just hiding behind it. But if you have almost equal, probably that is the almost equal impact will be there. Okay. So, that means if you have multiple taps in a system, and if something has shifted say 20 kilohertz, you can't guarantee that one particular tap has shifted 20 kilohertz. It may be one of them can be worst case, and that has been impacted more. But usually what happens, because all the taps will be equally impacted by the Doppler, right. It's obvious, right, because even if it is far off tap, Doppler can impact all of them. Suppose my receiver is moving. So, whether it is a nearby reflector or a far off reflector, the impact of the Doppler shift will be more or less the same. Okay. So, in a sense that all the taps in that case will give you the equal amount of power spectral density, not equal, maybe a similar amount of power spectral density. So, that is the kind of a very rough conclusion, but may not be very correct conclusions in this case. Okay. So, this is a very good way of modeling my Doppler part. Now, how do I do, I mean, what is the impact? I mean, is it like that the spectrum is of only interest to us? Isn't there anything else that I would like to have from this particular mathematical scenarios? Yes, there are many things that we can do it here. One thing that we can do it here is that, what about the channel estimation and tracking? For example, I know if there is a Doppler, there is a spectrum shift, but what does it buy to us? Does it buy anything to us? What will I do after knowing a spectrum shift? Does it really make a big deal for us? The big deal for us is the channel estimation, because that is the coefficient I need to know for my data detection. So, which means that even if I have H0, H0 m plus 1, H0 m plus 2 and I create a nice time series and do all these things, my final goal is not just the power spectral density of my changes, but rather I will be more interested to know what is the changed time, what is the changed channel coefficient at a particular time. That I am interested to know. So, which means that channel is changing. Suppose I have done a channel estimation, but it is suddenly changed at m plus 1. I may have to do a channel estimation. Channel again changes at m plus 2. I have to again do a estimation of my channel, because it has changed. Again channel changes. So, that means at every time do I have to do a channel estimation? That is the question we would like to answer. Is it required that at every point I need to do a re-channel estimation, re-estimation of my channel? Probably it is not required. What I need to know is that I need to know what value has become, right. So, what I am trying to say here is that the channel, say my Lth tap at m time, which is m time, it has become, or it has changed slightly, because as we know it is a correlated changes, right. It is not a very random change, it is a slight change, correlated change. At Lm plus 1 or m plus 2, the channel also changed slightly. Okay. Now, if it changes slightly, do I need to, first of all, do I really need to know whether channel has changed or not? So, first question I am asking here, do I need to consider that change? Okay. This is a very valid question. Suppose I am sampling at say 100 megahertz at my ADC, or my effective sampling rate is 100 megahertz, that is 0.01 microsecond. So, at every 0.01 microsecond, do I really need to know how much the channel has changed? Okay. First question. Second question is that if I think that changed value is of important to us, that means if I think that yes, whatever changed has happened, I would like to know how much change has happened. Okay. That means the channel has changed. Whatever value, suppose it was 1.23 value and this has become 1.2301, and say this has become 1.2302. The first question is this 1.2301 important to me, or is it significant to me? That is what I mean to say, important to me. Do I need to consider that change? Second aspect is that even if it changes to 1.2301, do I need to know this whole value? Let us say I need to know that. Point is that do I need to re-estimate this whole value, just the way I have done a channel estimation at mth time. So, what it means that at every time do I need to re-estimate my channel again and again and again? All these bulky algorithms that I may have deployed for channel estimation, do I really need to do that? The point is that if the answer is yes, then who will give you pilots? Because how do you estimate a data? I mean, without a pilot, estimating the channel is very difficult, right? Because that is the basic fundamental way of estimating channel. You can do a joint estimation of channel and data, as a blind estimation, but performance will be very poor. So, if I really want to get a very good estimation, I would always prefer a non-blind estimation, which means that every time I need to have a pilot to estimate my channel. That means I have a pilot here, I have a pilot here, I have a pilot here to re-estimate my channel. Then when will I send my data? Because every time I have to send a pilot only, right? Say I have to send one pilot or a data here. Suppose my channel is just a single, single antenna to single antenna, and every time I have to only send pilot only, right? There is no other way, because at P1 using P1 I estimate this channel. Fine, next time using another pilot I need to estimate, because that is a separate pilot. I have to, at that time whatever pilot comes, I cannot use my older data and estimate my HL minus m plus 1. Yeah. So, that means there is no data, I have to only estimate pilots. So, it is not possible, it is not feasible. So, which means that I cannot have the luxury to estimate my channel, re-estimate my channel completely using the fresh pilots again and again and again. That is not something that I can do. It is not virtually possible. So, the question that remains is that, can I have just one pilot here, which means I only observe data here and estimate my channel next without having a pilot there. Okay? If it is possible, how and what is the philosophy behind it? Yes, it is possible. So, this kind of concept is very much well known as a channel tracking. So, basically you estimate the channel and then you do not re-estimate fully, rather you only know how much the channel has changed, only the delta part you keep on estimating the delta part and readjust your channel, just a matter of readjustment. Why? Do I need to re-estimate the whole channel? Not required. Why it is not required? Because I know at m plus 1 my channel is a small delta from my previous data. That is precisely what I have shown it in the last classes, right? Because it is H0 at m plus 1 is nothing but whatever is H0 m plus some extra delta H. That is precisely happens here. There may be some factor here also. There may be a factor here also, but this is how the actually the channel is moving. At m plus 1 it is whatever was earlier plus some extra that random due to the Doppler that comes into picture. So, which means that essentially it forces me to think or model in a time series manner. So, it is in this particular case I have done an AR1 model, but I could have done different ARP or whatever model, but let us say I am just thinking in this very simplistic model. So, this is one interesting part, that at that m plus 1 I just create a simple AR1 model and say that, hey, the only thing I need to do is that I just have created a model, and now using this model can I guess HM plus, that is my job. My job is that I know this, I may know the statistics of it, can I guess this? That is the as simple as that. Okay? So, it is as if like you have a data called say D or observation called D, or this is your input data, or maybe you know that, and this is your noise data, and this is what your new data which you want to estimate it. Then I say x is equal to some sort of a D minus V. This is what my new data model, where D is your new data, say let us say that is your channel at m plus 1. This is my channel maybe at m, which I have estimated it. Now, this is my noise. So, my job is to re-estimate this H m plus 1 from this observation, because observation do not change. It is a very simple data model. So, this sort of you can use this kind of technique, or you can use normal estimation. So, this kind of way of I should not say it is a re-estimating, rather it is a readjustment of your channel. So, there is a new field, not a new field, there is a new dimension of thought, that is your adaptive signal processing, ASP. So, using adaptive signal processing you can you can actually I should not say re-estimate, rather you can readjust your new channel at m plus 1. Okay. So, this kind of thing you can you can call it a prediction. So, you have channel at m, I want to predict what it would be at m plus 1 using my old data. So, there is a different, I am not getting into that because that is completely a different direction of thought process. So, this time series is very important for us, either from a modeling point of view to know the spectrum, or to estimate my channel without getting any pilot, just to readjust my timings. So, this time series is very valuable in that aspect. Okay. Yeah, so we end it here. So, this is the reference book which contains the stationary time series. Thank you.